Hello, Math 2A class. This is Group 1, Ritika, Artemis, Zurich, and Masatika, and I'm artificial voice made in Apple. Since they can't speak as well as me, I'm gonna speak instead of them. This chapter is talking about some basic knowledge of differential equation and some techniques to solve first-order differential equations. Let's start. First, let's learn the basic terminology of any differential equation. Naming a differential equation includes order, coefficient, homogeneity, and partiality. The highest derivative of the function dictates the order of the differential equation. If all the coefficients of each term are constants or can be simplified to constants, then the dE is called constant coefficient EE, otherwise a variable coefficient. Also, if linear combination of function and its derivative is equivalent to 0, then it is called homogeneous dE, otherwise non-homogeneous dE. Then, if each term of dE does not contain product of the function or its derivatives, then it is called linear dE, otherwise nonlinear dE. And, if the function varies with only one independent variable, then it is an ordinary dE, otherwise it is called partial differential equation. Now, let's see some examples of differential equation, and guess the names of them. For the first one, the highest derivative is 1, the coefficient of each term cannot be simplified to constant. Also, the combination of function and its derivative is a function of x, therefore, it is a first-order variable coefficient non-homogeneous differential equation. For the second one, notice that it contains the product of the derivative. Therefore, it is a first-order nonlinear homogeneous differential equation. The third one contains more than one independent variables. Therefore, it is a partial differential equation. Next, let's solve very easy and basic first-order differential equations and see its applications. If you took calculus classes with a decent instructor, you have learned separation of variables technique to solve first-order dE. So, first, let's do a brief revision of this technique by a simple example and then go to its applications. Here is the example problem for separation of variable method. To solve this differential equation, first step is to separate the variables to both sides. Y terms go to the left side and x terms go to the right. Now, we have dy over radical 1 minus y squared equals to dx over radical x. Then, we integrate both sides to get y of x equals to sine of 2 radical x plus c. Notice that the boundary condition is provided as y of 0 is equals to 1/2. Plug it back to y of x. Solve for c equals to pi over 6. The solution to this differential equation is y of x equals to sine of 2 radical x plus pi over 6. Next, let's see some of the applications of first-order differential equation. The first application is population growth rate. Suppose constant birth rate is b, and death rate is d. For a short time interval delta t, bf of t delta t birth occurs, and df of t delta t death occurs. So, change in population is delta f, which is equal to b minus df of t delta t. By rearranging the equation and letting delta t approaching 0, we have f equal to b minus d times f. If b minus d is some constant k, then d over dt of f is k times f of t. The second application is Newton's law of cooling. This law suggests that the rate of change of temperature of an object with respect to time is proportional to the difference between the object's temperature and the surrounding temperature. The third application is Torricelli's law of draining tank. It suggests that the rate of change of volume of liquid in a draining tank, respects to time, is proportional to the square root of the depth water in the tank. Here, K is equal to the multiplication of area of hole in radical G. The figure shown depicts the variables in the equation, which are area of the hole, cross-section area, and the depth. Here, we need to pay attention at the depth, which is measured from the top of the tank till the hole opening. The fourth application is to find the position of swimmer who try to cross the river which has velocity. First, the model of river's velocity is given by velocity of river is equal to initial velocity of river times 1 minus x squared over a squared, where river's velocity plus minus a is equal to 0, and tangent of alpha is equal to velocity of river over velocity of swimmer, which is equal to dy dx. Substitute velocity of river as given in it. Then, we can get the first-order differential equation, which is dy dx is equal to initial velocity of river over swimmer's velocity times 1 minus x squared over a squared. The fifth application is that falling objects face air resistance. This can be modeled by first-order differential equation. Classically based on Newton's second law, summation of all the forces is equivalent to product of mass of the object and its acceleration. For low velocities, we can assume that the air resistance or drag force is proportional to the velocity, where n equals 1, and b is drag constant. The relation equation is F equal to negative b times v to the power of n. So, by applying Newton's second law, for constant mass, we have m times dv over dt is equal to mg minus bv. Next, let's see first-order linear differential equations. A first-order linear equation which is a of xy prime plus b of xy is equal to c of x is when the function f of x and y depends linearly on the dependent variable y only. This can be first-order variable coefficient non-homogeneous linear DE. The linear equation is of the form of x times y prime plus b of x times y equal to c of x. First we have to divide the entire equation by a of x so that it becomes y prime plus p of x times y equal to f of x. Here, we have replaced p of x instead of b of x over a of x, and f of x equal to c of x over a of x. There is a function called the integrating factor, such that when it is multiplied with the differential equation can be solved by separation of variables. Now, let's see how to find this integrating factor represented by mu of x. Multiply this by the differential equation. Now add and subtract mu prime of x times y. When we add and subtract mu of x times y, by rearranging all the terms, we get an equation in which mu prime of x minus mu of x times p of x has to be 0 in order to get the separation of variables equation of the form d over dx of some function equal to mu of x times f of x. So, now when we solve mu prime of x minus mu of x times p of x, we get mu of x equal to e to the power integration of p of x with respect to x. Finally, the solution of a linear equation is integrating factor times integration of mu of x times f of x with respect to x plus a constant c. Now, let's see the example. To solve this differential equation, y prime minus y equals to 2x times e to the power of 2x, with an initial condition y of 0 is equals to 1. First, we find the integrating factor, which is e to the power of the integral of p of x dx, where p of x is equal to negative 1. Therefore, the integrating factor, mu of x is equal to e to the power of negative x. Now multiply the equation with mu, and simplify it, to be e to the negative x times y prime minus e to the negative x times y equals to 2x e to the power of x. The left side of the differential equation must be the differentiation of product of integrating factor with the solution curve, if the integrating factor is correct. So, we can write the left side as the differentiation of e to the negative x times y is equal to 2x times e to the power of x. Now it becomes really easy to solve by using separation of variables. The solution then will be y of x equals to 2x times e to the power of 2x minus 2e to the 2x plus 3e to the power of x. Now is the time for some interesting applications. Simple solution mixture problems and basic circuit and series problems can be modeled by a first-order linear differential equations. Let's learn how to model them with f of t and its slope plus the non-homogeneous term. First application is the mixture problem. Suppose a tank with capacity V has V naught liter of solution with A naught amount of salt. At time 0, at the rate of R sub n liter per second, a salt solution with concentration of C sub n gram per liter pour into the tank, and after being completely mixed with the solution in the tank, some goes out at the rate of R sub out liter per second, with concentration C sub out equal to A naught divided by V naught, plus T times R sub n, minus R sub out. This equation is valid for T less than or equal to capital V minus V naught, divided by R sub n, minus R sub out. Since delta A is approximately equal to R sub n times C sub n, delta T minus R sub out times C sub out delta T, then limit of T goes to 0, is equal to dA over dt. Therefore, dA over dt is indirectly equal to r sub n times c sub n delta t minus r sub out times c sub out delta t. The differential equation here becomes dA over dt is equal to r sub n times c sub n delta t minus r sub out times a naught divided by v naught plus t times r sub n minus r sub out. The second application is Kirchhoff's second law, which states that the sum of the voltage drop across the capacitor and the resistor is equivalent to voltage source of the series circuit. The voltage drop across a capacitor is equal to charge, Q, over capacitance, C, and voltage drop across a resistor is equal to current, I, times resistance, R. So, the differential equation becomes R times dQ over dt plus Q times 1 over C, equal to V of t. Here, we discussed about RC circuit. Now, it's time for RL circuit. The voltage across an inductor is proportional to the rate of current through it. Recall the change of flux from your calculus class. So, voltage across an inductor is equal inductance L times di over dt. Therefore, by Kirchhoff's second law, we have L times di over dt plus Ri equal to V of t. This is the differential equation in circuit problem. Up to now, we have worked on linear differential equation. Now, let's learn how to solve a nonlinear differential equation, because it is sometimes possible to convert it to a linear differential equation by some transformation, and then solve it like we practiced before. First example is called Bernoulli differential equation, which can be written in the form of dy dx plus p of xy is equals to q of xy to the power of n. This ingenious method of solving by using transformation which we discuss here, was created by Leibniz in 1696. In this kind of equation, n is not equal to 1, therefore the equation is a nonlinear differential equation. In order to solve this kind of equation, we need to transform it into the form of the equation which we know how to solve. We let c equals to y to the power of 1 minus n, to change the equation into a linear differential equation. Then we can solve it by using the integrating factor, which we learned in previous slides. Let's see the example of Bernoulli's equation. To solve the Bernoulli equation dy dx plus y over x equals to y square, first we divide everything by y square. Then, we let c equals to y to the power of 1 minus n, where n is equal to 2. Therefore, z is equal to y to the negative 1. The equation now is written to be dz dx minus 1 over x times z equals to negative 1. Now, we have a linear differential equation, which we know how to solve by using integrating factor. In this case, the integrating factor is equal to e to the power of negative integral of 1 over x, which is 1 over x. Multiply the whole equation by the integrating factor and solve for z. Z over x equals to negative natural log of x plus some constant c. Notice that now the solution is for z. We have to transform it back to y. Therefore the final solution is y equals to 1 over x times constant c minus natural log of x. In previous slide, we learned about population growth and decay, and we assumed that the rate of change of population is proportional to the population with constant k. However, if k is a function of the population, then this is a nonlinear differential equation. A typical application of the logistic equation is a common model of population growth originally, due to Pierre-François Verhulst in 1838, where the rate of reproduction is proportional to both the existing population and the amount of available resources, all else being equal. He was unable to test the accuracy of his model because of inadequate census data, and he did not receive much attention until many years later. Reasonable agreement with experimental data was demonstrated by R. Pearl in 1930 for fruit fly population, and G. F. Howes in 1935 for flower beetle populations. This model is used in some topics such as Fermi distribution in physics, reaction models in chemistry, machine learning in statistics, growth of tumors in medicine, and diffusion of innovations in economics and sociology. Next method is called Riccati's equation, which was discovered by Euler in 1760. Following type of equation is called Riccati's equation. Y prime is equal to f of x plus p of xy plus q of xy squared. To solve Riccati's equation, first, we suppose that we know some particular solution y1. Then, we can obtain a general equation which is y is equal to y plus 1 over v of x. Third, you substitute above equation into Riccati's equation. Then, you can get a linear equation which is dv dx is equal to negative p of x plus 2q of x y 1 times v negative q of x. Now, let's see the example of Riccati. First, we suppose one of the solution is y1 equals to ax plus b. Substitute the solution and the derivative of it back in the differential equation. We have a equals to 1 plus x squared minus 2x times ax plus b square. Solve for the system. We have a equals to 1, and b equals 0. Back to the given solution and plug in a and b. We have y1 equals to x. Since for this kind of differential equation, we have general solution y equals to x, which is equal to y1, plus 1 over v of x p of x equals to negative 2x and q of x equals to 1. Simplify the above equation, we have dv dx equals to negative 1. This can be easily solved by separation of variables, and the solution is to be v equals to negative x. Therefore, the solution of the differential equation is y equals to x minus 1 over x. Next, let's see some another techniques to solve homogeneous differential equations. First technique is useful when a differential equation of the form p of x dx plus q of x dy equals to 0 is dimensionally consistent when the dimensionality of y is some power m of the dimensionality of x. Such equations are said to be isobaric, and the substitution y equals to u times x to the power of m reduces the equation to a separable differential equation. Let's solve a few examples. For problem A, first, we change the p of xy to p of ax and a to the power of m times y, which is equal to a to the power of r times x plus y, and also we change the q of xy to the formation as we discussed in previous slide. Then, we get the system equation as shown in the slide, by looking at the only p of x equation which transformed. To factor out a, m must be equal to 1. Then, we can get y is equal to x times u, substitute it into our original equation. Then, we can get the differential equation which can be solved by separation of variable. Another example, which is y squared dx minus x dy is equal to 0. Do the same step as above, and we can get the system of equation as shown in the slide, by looking at the only p of x equation which transformed. To factor out a, 2 meters must be equal to 1. Then, we can get m is equal to half. Plug into the y is equal to u times x to the power of m. We can get y is equal to square root of x times u. Substitute it into our original equation, get the easier differential equation, and solve it by using separation of variable. Note that after solving those equation by using u, you need to change back to x and y to get a correct solution. Next, let's take a look at exact differential equation. Let the function m, n, m sub y and n sub x be continuous in a simple connected region R, where there is no singularity. Then, m of x comma y dx plus n of x comma y dy is equal to 0, is an exact differential equation in region R, if and only if m sub y is equal to n sub x at each point in R. This means that there is a vector function capital F which is equal to m of x comma y as the vector in x direction, and n of x comma y as the vector in y direction. This function is conservative in region R. Now, to solve this type of DE, all you have to do is construct a function f of x and y, such that f of x and y is equal to integration of m with respect to x, plus the integration of n with respect to y, minus the integration of m sub y with respect to y. Let's see the example. To solve this differential equation, first we identify m to be 2xy minus 9x squared, and n to be 2y plus x squared plus 1. Then, we find the my and nx to see if the differential equation is exact or not. In this case, my equals to nx equals to 2x. So, the differential equation is exact according to the test. Then, we can use either the integral of m dx or n dy to find the f of x and y. However, we will need to be careful as this won't give us the exact function that we need. Often, it doesn't matter which one you choose to work with, while in other problems one will be significantly easier than the other. In this case it doesn't matter which one we use, as either will be just as easy. We then find out f of x and y is equal to x squared y minus 3x cubed plus some constant. Note that in this case, the constant of integration is not really a constant at all, but instead, it will be a function of the remaining variable, y in this case. Recall that, in integration, we are asking what function we differentiated to get the function we are integrating. Since we are working with two variables here, and talking about partial differentiation with respect to x, this means that any term that contained only constants or y's would have differentiated away to 0. Therefore, we need to acknowledge that fact by adding on a function of y instead of the standard c. Differentiate the function f of x and y, with respect to y and set it to n, since they must be 0 after all. From that, we can see the differentiation of h of y is equal to 2y plus 1. Integrate it, we then have h of y equals to y squared plus y plus some constant k. The function now is written as shown. However, we are not done yet. Recall from the beginning, we are given the initial condition, where y of 0 equals to -3. Plug it in, we can find the constant to be 6. The implicit solution is now y squared plus x squared plus 1 times y minus 3x cubed minus 6 equals to 0. If a differential equation m of x, y dx plus n of x, y dy equals to 0 is not an exact differential equation, then we cannot just solve it by integrating m dy or n dx. However, sometimes we can find an integrating factors that when we multiply the differential equation by it, we can make a non-exact differential equation into an exact differential equation. These integrating factors, if there is any, are not unique. So for a non-exact differential equation m of x, y dx plus n of x, y dy equals to 0, we multiply it by the integrating factor mu of x, y, then, we claim that this differential equation is an exact differential equation. Then, we take the partial derivative of both mu of x, y times m of x, y with respect to y, and y of x, y times n of x, y with respect to x, just like what we did when we were solving the exact differential equation. Since it is exact, mu y times m plus mu times my minus mu x times n minus mu times nx equals to 0. Then, we have to figure out what function mu is. First, let's say mu is a function of x only. Then n times d mu dx equals to my minus nx times mu. Using separation of variables, move mu to the left side, dx to the right, we have d mu over mu is equals to my minus nx over n. If this rational function is function of x only, then mu is equal to e to the power the integral of my minus nx over n dx. Or, let's assume mu is a function of y only. By doing the similar work, we find out the integrating factor mu should be e to the power of the integral of nx minus my over m dy. If the function mu is not only of x or y, but both, when taking the derivative of mu m and mu n, we take the partial derivative of mu with respect to y and x also. Therefore, negative d mu dy times m plus d mu dx times m equals to dm dy minus dn dx times mu. Move mu to the left side, we have the equation as shown. To integrate respect to only one variables, we introduce a z, which is a function of x and y. To make it solvable, the integrating factor can be calculated by mu of x, y equals to e to the power of the integral of dm dy minus dn dx over n, times dz dx minus m, times dz dy dz. Note that we need to transform z back to x and y when we are done solving the differential equation. Finally, this is the last technique for this chapter. There are some differential equations that can be reduced to homogeneous differential equations. For example, the differential equation shown above seems complicated. However, if we substitute y to z to the power of n, take the derivative of it, which is dy equals to n times z to the power of n minus 1 dz, plug them back in the dE, simplify it, and solve for the system, we have 2 plus 3n minus 1 equals to n minus 1, and also equals to 3n plus 1. Then, n is equal to negative 1. Plug it back in and simplify the equation to be negative x squared plus z squared dz plus 2xz dx equals to 1. Let z equals to xu. The equation then is u squared minus 1 times u dx plus x du plus 2u dx equals to 0. Solve to x times u squared plus 1 equals to cu and 1 plus x squared. times y squared equals to cy. Thank you for listening.